Okay, so it wanted us to write an expression of f in terms of k. So we plugged in our equation for where c was. You distributed, yes, of course, where you get 9/5 k, minus 2,457 divided by 5, and then you have plus 32 on the end. You added those last two pieces together. I'm going to give you the fraction and the decimal version, because I'm not sure which one you did. Okay, so fraction version, you get 9/5 k minus 2,297 over 5, or if you change those to decimals, you got 1.8k minus 459.4. So either one of those will work. It didn't tell you fraction or decimal, but it told you in terms of k, meaning k was the variable. Okay? So now, if you were a scientist doing scientist things, and you had the degrees in Kelvin, and you wanted to convert it into Fahrenheit, before, you would have to take your Kelvin, put it into Celsius, and then take Celsius and put it into Fahrenheit, right? This takes that middle piece away. Now I can put my Kelvin in and go straight to the Fahrenheit. Does that make sense? Okay. You composed two functions together into one. This is called a composition. Okay. This is a composition of a function. So yesterday we did operations with functions. We added them, we multiplied, we divided, we talked about domains. Okay. Today, what we're doing is and then we even evaluated, right? And I kind of gave you a hint. The evaluation part was what's going to help you with today. Okay? Because now, instead of plugging in a number, you're plugging in a whole function. Okay? Or if we're evaluating a composition, which we're going to do on our example 1, you plug a value into one function to get the output or the range, and then you take that and plug it into another function. So the range becomes the domain of another one. And then you evaluate it. Okay, so you work your way inside out. Okay, so we have two functions we're going to work with. Okay, we're either going to compose the functions together, or we're going to evaluate the functions together. Right? Okay. So you take the outcome of one to plug it in for the input of the next. Our first example, I'm going to show it to you as a table on how to evaluate compositions. Okay, so we have two functions. We have f of x equals the square root of 2x plus 1, and we have g of x equals x squared minus 4. Okay, what we're going to do is we are evaluating. So if I had asked you, and I'm going to show you how to read this out loud, g of f of 0. Okay, the table's going to help me do this. Okay, this is the evaluation of a composition we're going to do. Or if I wanted g of f of 4. Okay. Remember yesterday there was two different ways to write it, but they meant the same thing. This is two different ways to write composition. So you might see an open dot. It's not multiplying. It looks like a multiplication dot, but it's open. Okay, so that is showing composition. Okay. So what we're doing is we're going to plug 0 into f, get that outcome, and then plug that into g. And that'll be our final answer. Okay? We're going to take 4, plug it into f, get that answer, and then plug it into g. That's what that's telling you to do. So work from the inside out. So I'm going to do the table to help. We won't do a table every time, but I think the table gives a really good visual on what we're doing. Okay? So first we're taking our inputs, our domains of 0, 1, 2, 3, 4, and we're plugging them into f of x. F of x is the square root of 2x plus 1. You can do it by hand. You can do it by calculator. I don't care which one you do. I like making tables. So I'm going to go to my trusty dusty calculator. Go to y equals. I'm going to type in the square root of 2x plus 1, and I'm going to go to my table. And it shows me that an input of 0 will have an output of 1. An input of 1 will have an output of about 1.7. If I plug in 2, I'm going to get about 2.2. out of there. If I plug in 3, we get about 2.7. And if I plug in 4, I get 3. Okay, so that's evaluating for just f of x. We got that. We did that already. Old news. Okay. So I put 0 into f, and that outcome was a 1. Does that make sense? Here I plugged 4 into f, and my outcome was 3. So you're evaluating twice. So now you have a new input for your functions. What's up?
Questions like if you get this question like or something, are we required to turn the square root of a number that can't be square rooted into a decimal, or can we leave it as a square root of that number?
You would want to do the decimal because you're about to plug it into another function.
Okay.
So you would want to use decimals. I try to keep them nice and pretty. I can't promise that, but I do try. That's why I'm using 0 and 4 as the example, because that's what you would see tomorrow. Okay. So now we're going to take our outputs or our range values, and they become the new domain or inputs for g. So we're going to plug them in. Remember, g was what? X squared minus 4? Okay, so let's make this purple. X squared minus 4. So instead of an x, we're putting in our f of x. Okay, those are our new inputs. So it's going to be 1 squared minus 4, 1.7 squared minus 4, 2.2 squared minus 4, 2.7 squared minus 4, and 3 squared minus 4. This one you kind of have to type it in, and that's fine. You can do it. What's up? Square root of 3? Where do you see square root of 3? When x is 1?
And then if you put a square root of 3.
Okay.
If you did, let me find out this way. That's more. For the next part, let me start once you start getting this one.
Yes. You could. You're thinking a little. You're thinking deeper than I want you to, but you are correct. You're not wrong. Yes, you could do that. Okay. Yes, because when you round like I did, you do get more away from the exact answer, but that would be fine. We okay? Okay. So here we have negative 3. This gives me about negative 1.11. This gives me about 0.84. 3.29 and 5. I see what you're saying though. Because then my numbers would be better, wouldn't they? Did y'all see what he was saying? Here, I'm going to show you. Okay, so he's saying, so like 2 times 0, 0, plus 1, that's the square root of 1. That one's fine, right? It's just 1. 2 times 1 is 2, plus 1 is 3. So he's saying just leave this as the square root of 3. Because then this would be the square root of 3 squared, which is just 3 minus 4. So negative 1. I see what you like. Okay. 2 times 2 is 4, plus 1. Leave that as a radical of 5. So then the square root of 5 squared is 5. 5 minus 4 is 1. 2 times 3 is 6. 6 plus 1 is 7. So leave this as square root of 7. Square root of 7 squared is 7. 7 minus 4 gives me 3. And then my bottom one is good. Okay, yeah, let's do that. Because technically rounding takes you further away from the real answer. So if we leave it as a radical and we don't round, we are more true and more exact. So that works out. I like it. Thank you. The student becomes the teacher. Alright, so if I want g of f of 0, well, I know f of 0 is 1, and now what's g of 1? Negative 1. Right? At a g of f of 4, well, f of 4 gave me a 3, and g of 3 gives me 5. Wait, this is, hold up. This was the first one, so our outcome is negative 3. Plugging in 4 to begin with is this last one, which is 5. We're good? Okay. We won't make a table every time. Usually I'll just ask you for like one evaluation, but I want you to understand like how the process went. Okay. My next example, we're not evaluating, we are composing two functions together to get a new function. And then we're going to state the domain and range of that function. Okay. So we have f of g of x, part b is g of f of x, and part c is f of x. Alright, my f is 2x plus 5. My g is the square root of x minus 3. Okay. A and b, do you think they will equal the same thing? Maybe. We're not sure. Right? Do compositions, are they reversible, or does order matter? We're about to find out. Okay. So my first one says f of g. So that means we're going to take our f function, which is 2x plus 5. But instead of an x, what are we going to put in its spot? The g of x, which is the square root of x minus 3. Alright, here we're going to distribute, combine like terms, whatever we can do to simplify our equation. So 2 times the square root of x minus 3 is just going to be 2 times the square root of x minus 3, and we have plus 5. F of g of x equals. Okay, so that is my composition function. Now it wants me to find the domain and the range of the composition function. Okay, so what kind of function did we end up with? Is it a linear? Is it a cubic? What is it? It's a square root function, right? Do square root functions have restrictions on what they can be? Yeah, because they have that pot of gold, right? They have a starting point. This one's positive, so it's going to go up and over, right? So we need to know what that point is. Do you remember how to find that? This is like from before the break. Do you remember? Almost. Look inside the radical. If you took x minus 3 and made it equal to 0, you get x equals 3. And then 5. So your vertex, that's how you find your vertex of your square root. So I can't be anything lower than 3, right? And I can't be anything lower than 5. It does not exist. There's nothing to the left of the point. There's nothing under the point. So my domains are going to be all my x's as long as those x's are greater than or equal to 3. Makes sense, right? Because I can't have a negative. I can't square root a negative. If I plug 3 into there, 3 minus 3 is 0. That's as low as I can go. Okay? I can't plug in anything else lower than that because I'll end up with the square root of a negative number. Right? My range is, it's all of my y's, but I have a rule. Those y's must be greater than or equal to 5. Okay? So let's switch them. See if we get the same or something different. And get the domain and the range. Okay. So for g of f of x, and again I'm just going to show you that notation, it could also look like this. Okay, that's technically the same thing. You'll see that tomorrow. Just make sure you can recognize that those are telling you to do the same thing. We're plugging f into g. Okay, and x is staying x is not being changed to a number. Okay. My g function is the square root of x minus 3. So we're going to have the square root of, not x, it's going to be 2x plus 5. Okay. Here, when we combine like terms, all we get to do is do the 5 minus 3. So we get 2x plus 2. Did I get the same composition function? No. So does order matter with compositions? Absolutely. Yes. Order definitely matters. You have to make sure you follow the order. Okay? You work your way from the inside out. Okay? They're both square root functions, but it is not the same function. Okay? We did not get the same thing. So let's look at the domain and the range for this one. It is still a square root, so we're going to have restrictions going on. Where is our vertex for this square root function? Because you saw it behind me. Okay, so this is negative 1, 0. 2x plus 2, you make that equal to 0 and solve. Okay. 2x plus 2 equals 0. You subtract that 2 over, and then we divide. That's how I know x is negative 1. Now, where did the 0 come from? There's nothing over here, right? See how last time it was the plus 5 on the end? So 5 was my y. There's nothing there right now, so it's going to be 0. So my domain is going to be all x's, but what's the rule about my x's? They got to be greater than or equal to negative 1. How about the y's? Woo! Calm down, TV. Record. Alright, so we are plugging our f function into our f function. Combine like terms. This gives me what? 4x plus 10 plus 5, which gives me 4x plus 15 for my f of x. I don't like how that looks. f of x. There we go. Alright, what kind of function did we get this time? A linear function. Do we have any domain or range restrictions when it comes to linear functions? No. They go forever, right? This is a positive slope. It's going up like that. Nothing is stopping it. So how do I say everything? All real numbers. Remember, you can do your infinities, which Big Ideas likes to use. Or you can do that double-lined R. They mean the same thing. So I can go as low as negative infinity. I can go as high as positive infinity, is what that is showing us. Over here, we could, if you wanted to write it that same way, you could say negative 1 to infinity, is what that would look like. Remember doing like the brackets and stuff? This would be 0 to infinity. Would be how you could also write those out. All right. You feel okay?
Yeah.
All right, ready for the back?
Yes.
Another long day of notes, right? Sorry I gave you so much. All right, we're finally at our word problem. Modeling real life. Here we go. The function c of m equals 15 minus 10.5 m. It approximates the temperature in degrees Celsius at the altitude of m miles. The diagram shows the altitude in miles of an airplane t minutes after taking off, where t is the set of values over the interval 0 to 30. So it's showing you the first 30 minutes. This follows the first 30 minutes of the plane taking off. Okay? We're good? Because we agree, like, it doesn't go up forever. That's why it's giving me a time frame. After 30 minutes, the plane, levels off and goes straight. Okay, but it is ascending between those first 30 minutes of takeoff. All right, find C of m of t. Okay, well, I see the C function. Where's my m function? It's in my picture. Okay, so C of m of t. Okay, what is m of t? 0.2 t. So that's my m function. We're replacing m of t with the function 0.2. Now I get to take that and plug it into C, which is going to be 15 minus 10.5 times 0.2. Which is going to simplify to what? Negative 2.1 t. Oh, I forgot my t. There it is. Okay. So this represents the temperature in degrees Celsius, right? At a certain altitude, at a certain miles above ground after taking off so many minutes ago. So 3 things are being represented here. Evaluate C of m of 30 and explain what it represents. All right, so let's do m of 30 first. So 0.2 times 30 gives me what? Just 6. So 30 minutes, after 30 minutes, my altitude is 6 miles above the ground, right? Now we're going to take that and plug it into C. So my output becomes my input. 15 minus 10.5 times 6. Is that negative 63? So it gives me negative 48. Did I have to do all of that, by the way? Did I have to use both functions? Remember in my warm-up, instead of taking a degree and plugging it into one and then plugging it into the other, we found a composition of those 2 functions? Yes? So I made you do too much, but I'm proving a point. We found the composition from part A. So what if we did C of m of 30 using the equation that we just found? That gives me 15 minus 2.1 times 30, excuse me, which gives me 15 minus 63, look at that, negative 48. Okay, so that's the benefit. I'm sorry I made you do both. Okay, but that's the benefit of the composition functions. It's only one function you have to plug it into. You don't have to get something, plug it in, and get something again. Okay, it makes the steps actually less. Okay, so what does this mean? What is negative 48? The degrees, right? The degrees when? 30 minutes after takeoff. Good. 30 minutes after takeoff. The temperature is negative 48 degrees Celsius. That's what the composition function represents. Okay? Now doing it the 2 different steps does give me more information. It tells me the altitude. Right? It didn't ask me that, but if it asked me what was the altitude, you could tell me it was what? 6 miles. So that is a benefit of doing the extra work. But if you don't need to and it doesn't ask you for that, then you don't have to. We good? Easy enough, hopefully? Okay, good.